Okay, good morning. So, let me give a brief review of what we have done so far and what we plan to do going ahead. So, we started off with looking at some basics of Python, after which we moved to packages in Python like NumPy, Pandas, Matplotlib, Seaborn, Scikit-learn. We started data preprocessing. We saw what is preprocessing, how to clean data, transform data, integrate data, uh, join data from multiple data sources, and do feature engineering so that our data is then ready so that we can train machine learning algorithms using that preprocessed or prepared data. After which we saw different levels of algorithms. We started off with supervised learning, under which we saw classification. So we saw how machine learning works out for classification. We saw examples of KNN, decision tree, uh, uh, random forest, and naive Bayes, and so on. We saw how cross validation works. We saw how validation works. We saw about different metrics like accuracy, precision, recall, F1 score, F beta score, and we did some examples, a number of examples on classification. Then we moved on to something called as regression, which is again under the supervised learning bucket. We looked at how linear regression works out. We derived it using our equations. We saw how to implement it from scratch. We saw how our error function, how gradient descent works, and uh, we applied it on an example for housing price data. Then we moved towards unsupervised learning. We saw what is the use of unsupervised learning. We saw the major category within unsupervised learning is something called as clustering. We saw different approaches for clustering like exclusive and agglomerative, which for which we took examples of k-means and hierarchical clustering. We developed the code for k-means from scratch, and we looked at one data set, and that works out fine for k-mean. We looked at the student survey data, and that is off where we finished so far. Okay, there are multiple things we have done. We are now moving towards the next logical step after doing all this, and moving probably to our most complex topics so far, which is moving towards something called as neural networks. Okay. And neural networks is a very interesting topic, and uh, it opens a doorway into something more complex like deep learning. And uh, the main difference that has been till now and then moving ahead is basically our number of parameters goes on to such a large level that it becomes now very complex or very difficult to start to make sense of what the data is doing. Okay. So even though we can use neural networks well, and maybe we can understand to a good extent the math behind it, we lose sight on the parameters. We lose sight on what individual parameters are doing, and which is fine for now, so long as we are only interested in the answer. And it's a very interesting concept. It's a challenging concept, and it's a very powerful concept because we can do many things with neural networks that we cannot do with other shallow learning algorithms. Okay. So earlier, like maybe to my previous students, I would use your traditional slides method to try to teach neural networks. But recently, I found certain sets of videos and some material that is excellent. So it is uh, it is so nice that it is actually a shame if we don't use that material. Uh, I don't know if you have heard of this YouTube channel called as Three Blue One Brown, and this guy, he used to work with Khan Academy first, and then now he started out his own channel. And what I love about his videos is they are full of animations, that can help us visualize what is happening inside, what is happening in the background, especially when you're talking about neural networks. Because if we don't get a sense of what exactly is happening, we may get stuck into the maths and forget what is happening. Okay, so with that, maybe today I can start presenting from that video, and we can stop at strategic points, and we can discuss again, in a standard way of discussion, we could discuss what we understand, what we don't understand, and how we can take it better. But we will use the video as a reference, and I'll post the links to those YouTube videos in our channel, in our WhatsApp group, and then maybe for the next class you can view them beforehand, and when we come to the class we can simply start discussing. Okay, so let me share my screen for that video. Okay, just 1 second. I hope you are able to see my screen. Let me play the video. Let me know if you can hear the audio well. Okay.
This is a 3. It's sloppily written and rendered.
Is the audio okay? Okay, great. Let me take a little behind and start again.
This is a 3. It's sloppily written and rendered at an extremely low resolution of 28 by 28 pixels, but your brain has no trouble recognizing it as a 3. And I want you to take a moment to appreciate how crazy it is that brains can do this so effortlessly. I mean, this, and this are also recognizable as 3s, even though the specific values of each pixel is very different from one image to the next. The particular light-sensitive cells in your eye that are firing when you see this 3 are very different from the ones firing when you see this 3. But something in that crazy smart visual cortex of yours resolves these as representing the same idea, while at the same time recognizing other images as their own distinct ideas. But if I told you, hey, sit down and write for me a program that takes in a grid of 28 by 28 pixels like this, and outputs a single number between 0 and 10, telling you what it thinks the digit is, well, the task goes from comically trivial to dauntingly difficult. Unless you've been living under a rock, I think I hardly need to motivate the relevance and importance of machine learning and neural networks to the present and to the future. But what I want to do here is show you what a neural network actually is, assuming no background, and to help visualize what it's doing. Not as a buzzword, but as a piece of math. My hope is just that you come away feeling like the structure itself is motivated, and to feel like you know what it means when you read or you hear about a neural network quote-unquote learning. This video is just going to be devoted to the structure component of that, and the following one is going to tackle learning. What we're going to do is put together a neural network that can learn to recognize handwritten digits. This is a somewhat classic example for introducing the topic. And I'm happy to stick with the status quo here, because at the end of the 2 videos, I want to point you to a couple good resources where you can learn more, and where you can download the code that does this and play with it on your own computer. There are many variants of neural networks, and in recent years there's been sort of a boom in research towards these variants. But in these 2 introductory videos, you and I are just going to look at the simplest plain vanilla form with no added frills. This is kind of a necessary prerequisite for understanding any of the more powerful modern variants, and trust me, it still has plenty of complexity for us to wrap our minds around. But even in this simplest form, it can learn to recognize handwritten digits, which is a pretty cool thing for a computer to be able to do. And at the same time, you'll see how it does fall short of a couple hopes that we might have for it. As the name suggests, neural networks are inspired by the brain. But let's break that down. What are the neurons, and in what sense are they linked together? Right now, when I say neuron, all I want you to think about is a thing that holds a number, specifically a number between 0 and 1. It's really not more than that. For example, the network starts with a bunch of neurons corresponding to each of the 28 times 28 pixels of the input image, which is 784 neurons in total. Each one of these holds a number that represents the grayscale value of the corresponding pixel, ranging from 0 for black pixels up to 1 for white pixels. This number inside the neuron is called its activation. And the image you might have in mind here is that each neuron is lit up when its activation is a high number. So all of these 784 neurons make up the first layer of our network. Now jumping over to the last layer, this has 10 neurons, each representing one of the digits. The activation in these neurons, again some number that's between 0 and 1, represents how much the system thinks that a given image corresponds with a given digit. There's also a couple layers in between called the hidden layers, which for the time being should just be a giant question mark for how on earth this process of recognizing digits is going to be handled. In this network, I chose 2 hidden layers, each one with 16 neurons, and admittedly, that's kind of an arbitrary choice. To be honest, I chose 2 layers based on how I want to motivate the structure in just a moment. And 16? Well, that was just a nice number to fit on the screen. In practice, there is a lot of room for experiment with a specific structure here. The way the network operates, activations in one layer determine the activations of the next layer. And of course, the heart of the network, as an information processing mechanism, comes down to exactly how those activations from one layer bring about activations in the next layer. It's meant to be loosely analogous to how in biological networks of neurons, some groups of neurons firing cause certain others to fire. Now the network I'm showing here has already been trained to recognize digits, and let me show you what I mean by that. It means if you feed in an image, lighting up all 784 neurons of the input layer according to the brightness of each pixel in the image, that pattern of activations causes some very specific pattern in the next layer, which causes some pattern in the one after it, which finally gives some pattern in the output layer. And the brightest neuron of that output layer is the network's choice, so to speak, for what digit this image represents. And before jumping into the math for how one layer influences the next, or how training works,
okay, maybe let me summarize this so far. So what he's saying is neural networks are made up of neurons, and you see each of these circles here, they represent the neuron. As he says, neurons are basically stuff that holds a number. Okay, so some mathematical concept that holds a number, and neurons are connected from one to the other using these lines, and these lines are called as weights. Okay, for our case, we can assume that each neuron can be activated, and when we say it is activated, then it holds a number between 0 to 1. Okay, and the more the value, the brighter the neuron. The less the value, closer to 0, the darker the neuron. Okay, here we also see that there are multiple layers. So entire structure of network is made up of neurons actually, starting from input to the output. So the number of input nodes that we have, the number of input neurons that we have, depends upon our data. So in this case, the data here is an image. This image is made by 28 by 28 pixel data. Okay, so there are 28 rows and 28 columns, and each cell is called a pixel. That pixel can have a value between 0 to 1, which says again a value of 1 means it is bright white, a value of 0 means it is dark black, and if you see on these edges there are some middle terms that decides some shading. Okay, now we take all of these 28 by 28 and you put them into one giant column like this. So we take the first pixel here, that goes here. The next, in the same row, next pixel goes the second element. Same row, next pixel goes to the third element, and so on. So once we go to all 28, then we start again in the next row, and so on. That makes our 784 input neurons. In the next layer is called a hidden layer. We have 16 neurons here. The next layer again is second hidden layer, which is a 16 neurons. And the third layer is your output layer, which has 10 neurons. Okay. Our hope is this: when we input this 784 pixels of this handwritten 9 here to this model, we expect that in the output, the brightest one. Okay, so there are 10 outputs. The value of this 10th output, 9, will become 1, and everything else will become 0. Or this value will be closer to 1, and everything else will be closer to 0. That gives us one way of telling that this 9 has gone into the network has detected the answer, and it has given us this value as output. Okay, is this fine so far? Do you have any questions? Mm-hmm. Okay, it's clear. Then let me go ahead and play it. Okay.
Causes some very specific pattern in the next layer, which causes some pattern in the one after it, which finally gives some pattern in the output layer. And the brightest neuron of that output layer is the network's choice, so to speak, for what digit this image represents. And before jumping into the math for how one layer influences the next, or how training works, let's just talk about why it's even reasonable to expect a layered structure like this to behave intelligently. What are we expecting here? What is the best hope for what those middle layers might be doing? Well, when you or I recognize digits, we piece together various components. A 9 has a loop up top and a line on the right. An 8 also has a loop up top, but it's paired with another loop down low. A 4 basically breaks down into 3 specific lines and things like that. Now, in a perfect world, we might hope that each neuron in the second to last layer corresponds with one of these subcomponents. That anytime you feed in an image with, say, a loop up top, like a 9 or an 8, there's some specific neuron whose activation is going to be close to 1. And I don't mean this specific loop of pixels. The hope would be that any generally loopy pattern towards the top sets off this neuron. That way, going from the third layer to the last one just requires learning which combination of subcomponents corresponds to which digits. Of course, that just kicks the problem down the road, because how would you recognize these subcomponents or even learn what the right subcomponents should be? And I still haven't even talked about how one layer influences the next, but run with me on this one for a moment. Recognizing a loop can also break down into subproblems. One reasonable way to do this would be to first recognize the various little edges that make it up. Similarly, a long line, like the kind you might see in the digits 1 or 4 or 7, well, that's really just a long edge, or maybe you think of it as a certain pattern of several smaller edges. So maybe our hope is that each neuron in the second layer of the network corresponds with the various relevant little edges. Maybe when an image like this one comes in, it lights up all of the neurons associated with around 8 to 10 specific little edges, which in turn lights up the neurons associated with the upper loop and a long vertical line, and those light up the neuron associated with a 9. Whether or not this is what our final network actually does is another question, one that I'll come back to once we see how to train the network. But this is a hope that we might have, a sort of goal with the layered structure like this. Moreover, you can imagine how being able to detect edges and patterns like this would be really useful for other image recognition tasks. And even beyond image recognition, there are all sorts of intelligent things you might want to do that break down into layers of abstraction. Parsing speech, for example, involves taking raw audio and picking out distinct sounds, which combine to make certain syllables, which combine to form words, which combine to make up phrases and more abstract thoughts, etc. But getting back to how any of this actually works, picture yourself right now designing how exactly the activations in one layer might determine the activations in the next. The goal is to have some mechanism that could conceivably combine pixels into edges, or edges into patterns, or patterns into digits. And to zoom in on one very specific example, let's say the hope is for one particular neuron in the second layer to pick up on whether or not the image...
Okay, so let me quickly summarize. What he's saying is, why should a layered approach work well for a task like this? So the layered approach is actually showing different levels of abstraction. When you get an image like 9, detecting it is very complex. So we should start off with maybe just detecting small pieces of edges on the number. Okay, not just 9, but on all numbers, small edges. horizontal lines, vertical lines, slant of 30 degrees, slant of 45 degrees, slant of minus 35 degree, and so on. Once we have these edges, we can see how can these different combinations of these edges be combined to make more advanced concepts like loops and lines and horizontal lines, vertical lines, and so on. Once we have those loops and lines, we can see how those can combine to make linear numbers. And our hope is that probably the different layers of the network are doing this, not just for image recognition, but for all sorts of problems, like even for sound recognition or detecting what a person is speaking. The individual syllables will get detected. They get joined into 2-letter words, 3-letter words. They get joined into certain words that are making sense, and then ultimately they can join to make sentences and paragraphs and essays. So it says everything in the world, especially even all biological processes like we understand, are made up of smaller components that work well with bigger components, and then we have a working part. So our hope is this, that when we have a layered approach to neural networks, each layer is doing something very specific, starting from smaller concepts to larger concepts. And now he will go ahead and probably explain how this works out. Okay. If you have any question, you please stop me. Okay. And let me continue playing.
Has an edge in the mechanism that could conceivably combine pixels into edges, or edges into patterns, or patterns into digits. And to zoom in on one very specific example, let's say the hope is for one particular neuron in the second layer to pick up on whether or not the image has an edge in this region here. The question at hand is, what parameters should the network have? What dials and knobs should you be able to tweak so that it's expressive enough to potentially capture this pattern, or any other pixel pattern, or the pattern that several edges can make a loop, and other such things? Well, what we'll do is assign a weight to each one of the connections between our neuron and the neurons from the first layer. These weights are just numbers. Then take all of those activations from the first layer and compute their weighted sum according to these weights. I find it helpful to think of these weights as being organized into a little grid of their own, and I'm going to use green pixels to indicate positive weights and red pixels to indicate negative weights, where the brightness of that pixel is some loose depiction of the weight's value. Now, if we made the weights associated with almost all of the pixels 0, except for some positive weights in this region that we care about, then taking the weighted sum of all the pixel values really just amounts to adding up the values of the pixel just in the region that we care about. And if you really wanted to pick up on whether there's an edge here, what you might do is have some negative weights associated with the surrounding pixels. Then the sum is largest when those middle pixels are bright, but the surrounding pixels are darker. When you compute a weighted sum like this, you might come out with any number. But for this network, what we want is for activations to be some value between 0 and 1. So a common thing to do is to pump this weighted sum into some function that squishes the real number line into the range between 0 and 1. And a common function that does this is called the sigmoid function, also known as a logistic curve. Basically, very negative inputs end up close to 0, very positive inputs end up close to 1, and it just steadily increases around the input 0. So the activation of the neuron here is basically a measure of how positive the relevant weighted sum is. But maybe it's not that you want the neuron to light up when the weighted sum is bigger than 0. Maybe you only want it to be active when the sum is bigger than, say, 10. That is, you want some bias for it to be inactive. What we'll do then is just add in some other number, like -10, to this weighted sum before plugging it through the sigmoid squishification function. That additional number is called the bias. So the weights tell you what pixel pattern this neuron in the second layer is picking up on, and the bias tells you how high the weighted sum needs to be before the neuron starts getting meaningfully active. And that is just one neuron. Every other neuron in this layer is going to be connected to all 784 pixel neurons from the first layer. And each one of those 784 connections has its own weight associated with it. Also, each one has some bias, some other number that you add on to the weighted sum before squishing it with the sigmoid. And that's a lot to think about. With this hidden layer of 16 neurons, that's a total of 784 times 16 weights, along with 16 biases. And all of that is just the connections from the first layer to the second. The connections between the other layers also have a bunch of weights and biases associated with them. All said and done, this network has almost exactly 13,000 total weights and biases. 13,000 knobs and dials that can be tweaked and turned to make this network behave in different ways. So when we talk about learning, what that's referring to is getting the computer to find a valid setting for all of these many, many numbers so that it'll actually solve the problem at hand. One thought experiment that is at once fun and kind of horrifying.
Okay, let me take it a little back. Okay, do you remember this equation? Have you seen this before? Can you hear me? Okay. Have you seen this equation before in any of our algorithms?
Yes, weighted sum we have seen.
Which algorithm? Linear regression, right? Linear regression, right? Theta 1 x1 plus theta 2 x2 plus theta 3 x3, so on. This can be understood as theta 0 x0. And the sum of all these guys will give us our h theta of x, which is a linear regression hypothesis function. The additional thing that we have here is a sigmoid, which takes all of this and puts them into 0 to 1. So this is how your sigmoid works out. The sigmoid function is given by 1 plus e raised to minus x. If I have very small values of x, that is negative values of x, it will come closer to the answer of 0. If I have very high values, it will come closer to an answer of 1. And anything in between will just rise steadily. And at x is equal to 0, I will actually be cutting at the 0.5 point. Okay. And he also suggests that we have 13,002 different inputs, different parameters in this model. Okay. So 784 input neurons connect to all of these 784 input neurons will connect to the first one, the second one, and third one, and so on. Since we have 16 neurons in the next layer, 784 times 16 weights we will have to connect all these input layer neurons to the second layer of neurons. Then since we have 16 here, 16 times 16 gives us the next value, and then 16 times 10. So those are the weights that we have. And for each level of neuron, we have different biases. So here for these 16 neurons, we have 16 biases. 16 neurons, 16 biases here, and then 10 neurons, 10 biases here. So all of that gives us a total of, is, tell me, Anna.
What bias? I didn't get that part. Weight is fine, but bias.
Yeah, bias is just a term that tells us when do we consider this neuron to be activated. Okay, so if I take all the inputs that go here, multiplied by all of these weights, you'll get this number. And if you want zero bias, you would say that whenever this number is positive, I will say that this is activated. Whenever this number is negative, I will say that this is closer to 0. But sometimes I would want to have a threshold that only after the sum is greater than 10 or only after the sum is greater than 5, that is the point when I start considering that this is active. So that is the bias we have here. If you compare this with our linear regression task, we had a bias term or a base term, which was the average of all the inputs for okay, for our target variable. So we would say, let's say our house price data. We say the different features that we have are square feet, number of rooms, garages, and so on. And house price, I will have a bias term, an average term. That is, I take all of my data points and I find what is the average house price. Now that does not take into account any of the features, but gives me one number to start with. So here also the bias represents that value. It gives you that one value to start with that tells us that, okay, if at least the output is lit up to some extent, we would consider this as a bias and go on. Okay. So bias is also, you could consider bias is also a parameter that we are trying to train. So here it gives us 13,000 different parameters. Just try to compare with all the examples that we have seen so far. We have never found an example with so many different parameters, right? Our parameters are generally of the order of 5 to 10 different parameters that we play with. But now we've got almost 13,000 different parameters. So that's a huge change in our approach. Okay. I hope you got this right. Do you have any questions?
It's clear. Got it.
Okay, let me go ahead.
Will actually solve the problem. Because when the network tweaked and turned to make this network behave in different ways. So when we talk about learning, what that's referring to is getting the computer to find a valid setting for all of these many, many numbers so that it'll actually solve the problem at hand. One thought experiment that is at once fun and kind of horrifying is to imagine sitting down and setting all of these weights and biases by hand, purposefully tweaking the numbers so that the second layer picks up on edges, the third layer picks up on patterns, etc. I personally find this satisfying rather than just treating the network as a total black box, because when the network doesn't perform the way you anticipate, if you've built up a little bit of a relationship with what those weights and biases actually mean, you have a starting place for experimenting with how to change the structure to improve. Or when the network does work, but not for the reasons you might expect, digging into what the weights and biases are doing is a good way to challenge your assumptions and really expose the full space of possible solutions. By the way, the actual function here is a little cumbersome to write down, don't you think? So let me show you a more notationally compact way that these connections are represented. This is how you'd see it if you choose to read up more about neural networks. Organize all of the activations from one layer into a column as a vector. Then organize all of the weights as a matrix, where each row of that matrix corresponds to the connections between one layer and a particular neuron in the next layer. What that means is that taking the weighted sum of the activations in the first layer, according to these weights, corresponds to one of the terms in the matrix vector product of everything we have on the left here. By the way, so much of machine learning just comes down to having a good grasp of linear algebra, so for any of you who want a nice visual understanding for matrices and what matrix vector multiplication means, take a look at the series I did on linear algebra, especially chapter 3. Back to our expression, instead of talking about adding the bias to each one of these values independently, we represent it by organizing all those biases into a vector and adding the entire vector to the previous matrix vector product. Then as a final step, I'll wrap a sigmoid around the outside here. And what that's supposed to represent is that you're going to apply the sigmoid function to each specific component of the resulting vector inside. So, once you write down this weight matrix and these vectors as their own symbols, you can communicate the full transition of activations from one layer to the next in an extremely tight and neat little expression. And this makes the relevant code both a lot simpler and a lot faster, since many libraries optimize the heck out of matrix multiplication. Remember how earlier I said these neurons are simply things that hold numbers? Well, of course, the specific numbers that they hold depends on the image you feed in. So it's actually more accurate.
Okay. So here just he is transferring all of the different inputs and weights we have into a vectorized notation. This is again very similar to what we did for linear regression as well. We saw that, okay, if we have so many weights and if you're trying to do gradient descent, doing it in a for loop may be complicated for multiple things, for representing the idea first, and then additionally for computation also. If you have many parameters that you want to play with, computation will become very hefty or hectic to do. So once we have a reduced representation, many algorithms are very optimized to work on matrices. which can help us in getting the answer rightly. Also, implementing it in code is easier. Plus, understanding what it is doing is also easier. So it makes total sense to write this down into linear algebra. There's actually one part that I wanted to comment upon, which happened earlier, is this part where we're trying to come up with trying to understand what the weights should be, so that we are able to detect just a horizontal edge somewhere on the top side of this image. Okay, so I'm not sure if you've understood this. Let me try to put it in my terms to just give an understanding. Okay, so here, this is the input layer. These are the 784 different inputs that will go here, 28 by 28. Each of the neurons in the next layer are connected to each of the input layer using these weights. We are assuming that one of these neurons is a neuron that detects this edge here. Okay, so how would we put the values of these weights? Of course, we will not do this manually, but as a thought experiment, how would we put the values of these weights so that we can detect a positive edge here? So we can detect a horizontal edge here. What he's suggesting is, what we could do is we could put all of the weights as 0, except for this part. Okay, that is the weights that will the input neurons where we want light to be there, we will put our weights as positive, and everything else will keep as 0. So when we evaluated this weighted sum, what will happen is, each of these pixels, the first pixel will get multiplied with the second pixel. First pixel here will get multiplied with the first pixel here, and so on. So all of these guys will give us 0, except for the terms in between. These terms will give us a positive number, which suggests to us that there is some value here. Okay, I'm not interested what is happening everywhere else in the board, but on this region, I'm interested to find out if there are ones. Okay, and if we multiply these two guys, we will get some summation value, and we can say, okay, if that summation is greater than a particular number, we could assume that this image has an edge at this point. Now, this edge can come also if this. So if I have all the pixels on this board as white, then also we'll get the same answer. So he suggests an additional way. Along with this green, we will put a negative weights on the top and bottom. What we expect now is that there should be an edge. That means these are white pixels, but not white everywhere. There are black pixels on the top, black pixels on the end here. And that would give us some better confidence that we are detecting an edge here. Okay, so it's an idea of how the neural network may work. Okay, internally. Let me go back to where we were. Okay.
Of matrix multiplication. Remember how earlier I said these neurons are simply things that hold numbers? Well, of course, the specific numbers that they hold depends on the image you feed in. So it's actually more accurate to think of each neuron as a function, one that takes in the outputs of all the neurons in the previous layer and spits out a number between 0 and 1. Really, the entire network is just a function, one that takes in 784 numbers as an input and spits out 10 numbers as an output. It's an absurdly complicated function, one that involves 13,000 parameters in the forms of these weights and biases that pick up on certain patterns, and which involves iterating many matrix vector products and the sigmoid squishification function. But it's just a function nonetheless. And in a way, it's kind of reassuring that it looks complicated. I mean, if it were any simpler, what hope would we have that it could take on the challenge of recognizing digits? And how does it take on that challenge? How does this network learn the appropriate weights and biases just by looking at data? Well, that's what I'll show in the next video, and I'll also dig a little more into what this particular network we're seeing is really doing. Now is the point I suppose I should say subscribe to stay notified about when that video or any new videos come out, but realistically, most of you don't actually receive notifications from YouTube, do you? Maybe more honestly, I should say subscribe so that the neural networks that underlie YouTube's recommendation algorithm are primed to believe that you want to see content from this channel get recommended to you. Anyway, stay posted for more. thank you very much to everyone supporting these videos on Patreon. I've been a little slow to progress in the probability series this summer, but I'm jumping back into it after this project, so patrons, you can look out for updates there. To close things off here, I have with me Leisha Lee, who did her PhD work on the theoretical side of deep learning, and who currently works at a venture capital firm called Amplify Partners, who kindly provided some of the funding for this video. So, Leisha, one thing I think we should quickly bring up is this sigmoid function. As I understand it, early networks use this to squish the relevant weighted sum into that interval between 0 and 1, kind of motivated by this biological analogy of neurons either being inactive or active.
Exactly.
But relatively few modern networks actually use sigmoid anymore.
Yeah.
That's kind of old school, right?
Yeah, or rather, ReLU seems to be much easier to train.
And ReLU stands for rectified linear unit?
Yes, it's this kind of function where you're just taking a max of 0 and a, where a is given by what you were explaining in the video. And what this was sort of motivated from, I think, was partially by a biological analogy with how neurons would either be activated or not. And so if it passes a certain threshold, it would be the identity function. But if it did not, then it would just not be activated, so it'd be 0. So it's kind of a simplification. Using sigmoids didn't help training, or it was very difficult to train at some point, and people just tried ReLU, and it happened to work very well for these incredibly deep neural networks.
All right, thank you, Leisha. For background, Amplify Partners, an early-stage VC, invests in technical founders building the next generation of companies focused on the applications of AI. If you or someone that you know has ever thought about starting a company someday, or if you're working on an early-stage one right now, the Amplify folks would love to hear from you. They even set up a specific email for this video, 3blue1brown@amplifypartners.com, so feel free to reach out to them through that.
Okay. So the end part was just talking about another option for using sigmoid. So that could be one of the hyperparameters that we use. If our activation is sigmoid or ReLU. As they said, ReLU is faster to learn. We don't know why it works, actually. I've read some material, but we hardly understand why ReLU works better than sigmoid, but it does similar tasks where we are trying to convert our summation, which may give out some number, into a range of different values. Okay, is this fine so far? Do you have any questions? Okay, in that case, let me open the next video.
Last video, I laid out the structure of a neural network. I'll give a quick recap here, just so that it's fresh in our minds, and then I have two main goals for this video. The first is to introduce the idea of gradient descent, which underlies not only how neural networks learn, but how a lot of other machine learning works as well. Then after that, we're going to dig in a little more to how this particular network performs, and what those hidden layers of neurons end up actually looking for. As a reminder, our goal here is the classic example of handwritten digit recognition, the hello world of neural networks. These digits are rendered on a 28 by 28 pixel grid, each pixel with some grayscale value between 0 and 1. Those are what determine the activations of 784 neurons in the input layer of the network. And then the activation for each neuron in the following layers is based on a weighted sum of all the activations in the previous layer plus some special number called a bias. Then you compose that sum with some other function, like the sigmoid squishification or a ReLU, the way that I walked through last video. In total, given the somewhat arbitrary choice of 2 hidden layers here with 16 neurons each, the network has about 13,000 weights and biases that we can adjust. And it's these values that determine what exactly the network, actually does. Then what we mean when we say that this network classifies a given digit is that the brightest of those 10 neurons in the final layer corresponds to that digit. And remember, the motivation that we had in mind here for the layered structure was that maybe the second layer could pick up on the edges, and the third layer might pick up on patterns like loops and lines, and the last one could just piece together those patterns to recognize digits. So here, we learn how the network learns. What we want is an algorithm where you can show this network a whole bunch of training data, which comes in the form of a bunch of different images of handwritten digits, along with labels for what they're supposed to be, and it'll adjust those 13,000 weights and biases so as to improve its performance on the training data. Hopefully, this layered structure will mean that what it learns generalizes to images beyond that training data. And the way we test that is that after you train the network, you show it more labeled data that it's never seen before, and you see how accurately it classifies those new images. Fortunately for us, and what makes this such a common example to start with, is that the good people behind the MNIST database have put together a collection of tens of thousands of handwritten digit images, each one labeled with the numbers that they're supposed to be. And as provocative as it is to describe a machine as learning, once you actually see how it works, it feels a lot less like some crazy sci-fi premise, and a lot more like, well, a calculus exercise. I mean, basically it comes down to finding the minimum of a certain function. Remember, conceptually, we're thinking of each neuron as being connected to all of the neurons in the previous layer, and the weights in the weighted sum defining its activation are kind of like the strengths of those connections. And the bias is some indication of whether that neuron tends to be active or inactive. And to start things off, we're just going to initialize all of those weights and biases totally randomly. Needless to say, this network is going to perform pretty horribly on a given training example, since it's just doing something random. For example, you feed in this image of a 3, and the output layer, it just looks like a mess. So what you do is you define a cost function, a way of telling the computer, no, bad computer, that output should have activations which are 0 for most neurons, but 1 for this neuron. What you gave me is utter trash. To say that a little more mathematically, what you do is add up the squares of the differences between each of those trash output activations and the value that you want them to have. And this is what we'll call the cost of a single training example. Notice, this sum is small when the network confidently classifies the image correctly, but it's large when the network seems like it doesn't really know what it's doing. So then what you do is consider the average cost over all of the tens of thousands of training examples at your disposal. This average cost is our measure for how lousy the network is and how bad the computer should feel. And that's a complicated thing. Remember how the network itself was basically a function, one that takes in 784 numbers as inputs, the pixel values, and spits out 10 numbers as its output. And in a sense, it's parameterized by all these weights and biases. Well, the cost function is a layer of complexity on top of that. It takes as its input those 13,000 or so weights and biases, and it spits out a single number describing how bad those weights and biases are. And the way it's defined depends on the network's behavior over all the tens of thousands of pieces of training data. That's a lot to think about. But just telling the computer what a crappy job it's doing isn't very helpful. You want to tell it how to change those weights and biases so that it gets better. To make it easier, rather than struggling to imagine a function with 13,000 inputs, just imagine a simple function that has one number as an input and one.
Okay, so maybe let me quickly summarize this part. What he's saying is, once we pass our inputs through this model, we start off initially by choosing these weights and biases randomly. Okay, since we choose this randomly, we would expect that the output layer would not have the right answer. It will have a mix of all bright values, and that is fine at this point, because our network is not yet trained. So just imagine our scenario with linear regression, where we start off the model with random values of data. And what ends up happening is, from our first iteration, our prediction is very bad compared to the output. But that is expected. Now, in the next level, what we have to do is we have to take all the outputs for all the different inputs. What is our model predicting as output? Once we have all of those outputs, we will compare that with all of the actual outputs that we want. Since we are working in supervised learning, we have the labels for the data that we have. And comparison with that label gives us, comparison of our prediction with the label gives us the error, the square of the error, and then summation of all these errors for summation of all these points gives us what is our cost for that sample. Now, we don't do it for one sample, we do it for all the samples within our data set. So if there are thousands of images, we take the average cost over all the costs, and we'll say that is the error of our model, or that is the cost of our model. And our hope is that we would want to reduce this cost in a way so that by changing the weights and parameters. So by changing the weights and parameters, we hope that our cost will become less. When our cost becomes less, we can see that our output layer will start looking like this. So when you put a 3 inside, you would see that only one bright light at 3 and everywhere else it will be dark. And that is our hope. For that, we are doing this process of evaluating the cost and then doing something with it. Something with it is, of course, gradient descent, which he will talk about very shortly. So let me wait till that point and go ahead. Okay.
Isn't very helpful. You want to tell it how to change those weights and biases so that it gets better. To make it easier, rather than struggling to imagine a function with 13,000 inputs, just imagine a simple function that has one number as an input and one number as an output. How do you find an input that minimizes the value of this function? Calculus students will know that you can sometimes figure out that minimum explicitly, but that's not always feasible for really complicated functions. Certainly not in the 13,000 input version of this situation for our crazy complicated neural network cost function. A more flexible tactic is to start at any old input and figure out which direction you should step to make that output lower. Specifically, if you can figure out the slope of the function where you are, then shift to the left if that slope is positive, and shift the input to the right if that slope is negative. If you do this repeatedly, at each point checking the new slope and taking the appropriate step, you're going to approach some local minimum of the function. And the image you might have in mind here is a ball rolling down a hill. And notice, even for this really simplified single input function, there are many possible valleys that you might land in, depending on which random input you start at. And there's no guarantee that the local minimum you land in is going to be the smallest possible value of the cost function. That's going to carry over to our neural network case as well. And I also want you to notice how if you make your step sizes proportional to the slope, then when the slope is flattening out towards the minimum, your steps get smaller and smaller, and that kind of helps you from overshooting. Bumping up the complexity a bit, imagine instead a function with 2 inputs and 1 output. You might think of the input space as the xy plane, and the cost function as being graphed as a surface above it. Now, instead of asking about the slope of the function, you have to ask which direction should you step in this input space so as to decrease the output of the function most quickly. In other words, what's the downhill direction? And again, it's helpful to think of a ball rolling down that hill. Those of you familiar with multivariable calculus will know that the gradient of a function gives you the direction of steepest ascent. Basically, which direction should you step to increase the function most quickly? Naturally enough, taking the negative of that gradient gives you the direction to step that decreases the function most quickly. And even more than that, the length of this gradient vector is actually an indication for just how steep that steepest slope is. Now, if you're unfamiliar with multivariable calculus and you want to learn more, check out some of the work that I did for Khan Academy on the topic. Honestly though, all that matters for you and me right now is that in principle there exists a way to compute this vector. This vector that tells you what the downhill direction is and how steep it is. You'll be okay if that's all you know and you're not rock solid on the details. Because if you can get that, the algorithm for minimizing the function is to compute this gradient direction, then take a small step downhill, and just repeat that over and over. It's the same basic idea for a function that has 13,000 inputs instead of 2 inputs. Imagine organizing all 13,000 weights and biases of our network into a giant column vector. The negative gradient of the cost function is just a vector. It's some direction inside this insanely huge input space that tells you which nudges to all of those numbers is going to cause the most rapid decrease to the cost function. And of course, with our specially designed cost function, changing the weights and biases to decrease it means making the output of the network on each piece of training data look less like a random array of 10 values and more like an actual decision that we want it to make. It's important to remember, this cost function involves an average over all of the training data. So if you minimize it, it means it's a better performance on all of those samples. The algorithm for computing this gradient efficiently, which is effectively the heart of how a neural network learns, is called backpropagation, and it's what I'm going to be talking about next video. There, I really want to take the time to walk through what exactly happens to each weight and each bias for a given piece of training data, trying to give an intuitive feel for what's happening beyond the pile of relevant calculus and formulas. Right here, right now, the main thing I want you to know, independent of implementation details, is that what we mean when we talk about a network learning is that it's just minimizing a cost function. And notice, one consequence of that is that it's important for this cost function to have a nice, smooth output, so that we can find a local minimum by taking little steps downhill. This is why, by the way, artificial neurons have continuously ranging activations, rather than simply being active or inactive in a binary way, the way that biological neurons are. This process of repeatedly nudging an input of a function by some multiple of the negative gradient is called gradient descent. It's a way to converge towards some local minimum of a cost function, basically a valley in this graph. I'm still showing the picture of a function with two inputs, of course, because nudges in a 13,000 dimensional input space are a little hard to wrap your mind around, but there is actually a nice non-spatial way to think about this.
Okay, so basically the task of neural network comes down to evaluating a cost function and finding out the minimization of that cost function. Okay, when you're in a single dimension problem, then we can directly find the slope at a point by using calculus. So derivative at a point gives us the slope, and that slope can help us to identify if we want to increase or reduce our number so that we reach to the minimum value. When you're talking in a two-dimensional space, that slope becomes a gradient. In fact, from any dimension above 1, it becomes a gradient of different sizes. So he showed an example of a two-dimensional space, which is easy to probably understand and see what is happening. Even there, our hope is that we want to find that point which gives us the minimum cost. A gradient gives us the direction in which we want to move. We need to move. And not just the direction, it also gives us a magnitude on how steep is the curve at that point. So exactly or very similar to what we saw in linear regression. But here the only difference is our gradient includes 13,002 different dimensions, which is a huge number. So it is impossible to visualize. But he suggests, or this guy gives us a way of understanding what these numbers mean. Okay, and that will be the next part basically. We'll stop here for today, and I will forward the links of these videos to our group. Probably coming next time in the next class, if you could view them and come, then it would help us to be a little more faster. Okay. Before stopping, do you have any questions? Okay, great. Then let's stop here. I will stop sharing and stop recording.